So I know you must be wondering what I do all day. I put out these videos and they're only like 5 or 8 minutes long. You're like, what is he doing for the rest of the day? They're filled with bad outtakes, things that I am so embarrassed that are in front of the camera that I just keep redoing and retaking and retaking and retaking. And so an 8 minute film is taking many hours. It's ridiculous. Well, today we're going to be talking about radioactive decay and, in particular, half lives. And this is going to sum up our discussion in nuclear physics. And this is exactly the same as chemistry half lives and chemistry decay. So if you've already had chemistry and you want to just go try the homework, that's fine. If you can't remember how to do it, or this is new to you, stick around and we'll show you. It's not that hard. So what is a half-life? Well, let's say that I have 10 grams of radioactive carbon. I don't know. We'll make it up. After two half-lives have transpired, the amount of radioactive material has been halved twice because it's two half-lives. So after a single half-life, that 10 grams of radioactive material will now be 5 grams of radioactive material. And 5 grams of non-radioactive material, by the way. It doesn't just disappear into thin air. It just goes non-radioactive. And then half of what remains after that, of that 5 grams, after another half-life, would go. So after two half-lives, we'd expect 2.5 grams of this radioactive material to remain. So if that seems really convoluted, it's okay. Some of the math does a lot of this thinking for you. The thing you should get in your head, or the picture you should get in your head, is that as time goes by, the amount of radioactive material in a rock or in a piece of cloth or whatever it is doesn't just drop off abruptly. There's this inverse exponential curve of decay that takes place. And so at first, you lose a lot of radioactive material, but then over time, the amount that you lose per year gets less and less and less and less. So using the tools in this section, you can do things like carbon dating and things like that if you were into that type of thing. We just cover this more from an idealistic physics perspective, and so we don't stress too much about that. So let's go ahead and just dive into the math if that's okay. So half lives. Here we go, radioactive half lives. So the formula that you're going to see the most often is this one, and that is that the fraction of the substance which remains radioactive after some time is equal to 1/2 half-life raised to the t divided by half-life. So this here is the half-life of the substance in question. This is the fraction that remains of that radioactive material, and t is the elapsed time. It's a fairly simple formula to use, especially if you're just trying to solve for the fraction. Sometimes you'll see it this way. Other times I've seen other textbooks present it different ways. Here's one that appears in a textbook I'm familiar with. Talk about the mass of a substance that's still radioactive after some time. That is equal to the mass that you had originally, again, times this factor that we just barely introduced in the equation above. So this is the original mass, or the original number of nuclei, alternatively. And this is mass after time t. Okay, and then again, this is the half-life, right? Hooray. So again, if you're trying to solve for things like how much of the radioactive substance is left after a certain amount of time, this is actually fairly easy and straightforward to do. Sometimes they ask you to solve for the half-life itself, in which case you have to use the properties of logs to solve. And so we'll do an example like that at the end of this video. Let's first do the straightforward example that you probably are pretty familiar, or would be more comfortable with, I guess. So let's say that I have 100 grams of zinc 71. Okay, and it turns out the half-life for zinc 71 is 2.4 minutes. So the question is, how much of this zinc 71, this 100 grams, remain after, I don't know, 7.2 minutes? Okay, so I'm just going to plug things into an equation here. notice they're giving me masses inside of the problem, and so I'm going to use the equation that uses masses, and that's this one. They're asking for the amount of zinc that remains, so that's what the M there represents. M naught is the original mass of zinc, that's the 100 grams, and then they gave me the half-life, which is specific to the substance, as 2.4 minutes. So let's just plug things in and see where this ends up. So the mass after time t, M, is going to be equal to 100 grams times 1/2 times, we're going to say 7.2 minutes. We're going to divide that by the half-life that they gave me in the problem. That's 2.4 minutes. Notice that in this ratio right here, the units have to be the same. Otherwise, the units won't cancel. So just be advised that that has to be the case. We don't give you problems like that would throw you off, but just kind of make sure that's the case. So how much is remaining? Well, by the way, this looks like that's 3 half-lives there. If we throw this into our calculator, it's like we halved 103 times. So it turns out we get 12.5 grams. 12.5 grams of that radioactive substance would still be around after 7.2 minutes. Okay. All right, let's do one that's a little bit trickier that requires properties of logs. So let's say that I have, that we've waited 24 days. And after 24 days, 2 milligrams of 128 milligrams remain of a radioactive substance. The question is, what is the half-life? Okay, so let's kind of be efficient here. I'm going to plug things in again to that mass formula, because notice they're giving me masses in terms of milligrams here. So again, we're going to use this formula here to take this out. And here we have it. 2 milligrams is equal to 128 milligrams. I'm going to multiply this again by that factor 1/2 times T over T naught. We've waited 24 days. And we are looking for the half-life. That is what we want. So the question is, how on earth do we get to that half-life if it's stuck up there in the exponent? So let's practice that first of all. What I'm going to do is I'm going to try to work on isolating this half-life by first dividing both sides by 128 milligrams. So we have 2 milligrams divided by 128 milligrams. And I'm going to suppress units for right now on this side. So this is what we have so far. Because the unknown is in the exponent, we use logs to get that down. And so I'm going to take the natural log of both sides. So here we go. There's the natural log. And so what I have is the natural log of 2 divided by 128 is equal to the natural log of 1/2 raised to the 24 divided by the half-life. So what I'm going to do now is we're going to use the properties of logs. I'm going to take down that exponent now. So I have 24 times t 1/2. And this is sort of what we end up with. So properties of logs allow you to do this. If something's in an exponent, that's inside of a log argument, that's the same as bringing it out front as a multiplicative factor. And that's something that we look at in Math 1050. This is still kind of hard to get to though, so I'm gonna switch this guy and this guy's spots, multiply both sides by the half-life, and divide by the natural log of 2 divided by 128. Sorry. And so we're going to get that the half-life then is equal to 24 times the natural log of 1/2 divided by the natural log of 2 over 128. And the answer that we get is 4 days. The reason I knew it was in days is that the time unit they gave me inside of the problem was days 2, and so I just carried that unit through knowing that they had to be the same unit. So That's it. That's radioactive decay. If you happen to have problems on the HOMIC, let me know, but this tends to be pretty straightforward, so I'll let you have at it.